Hello everybody, this is my first podcast for the course of computational geometry, and today we're going to cover chapter 2. It's essentially we're going to develop an algorithm to find all the intersections of a series of lines that are in the plane, and we're going to find an algorithm that has a decent complexity, which means that it is here we are looking for a complexity that is n log n, where n is the number of lines which are present in the plane. It's not exactly that. I'm going to be more clear about that. But first, let's present the problem. And here we have a series of lines. Okay, so a series of lines, and we're going to give them names. Okay, this is S1, S2, like segments, S3, S4, okay, and that's S4, there's only 4 lines. Okay, that's 4 lines, and we will, to find all their intersections, all the points that are the intersections of 2 separate lines. Here, I'm going to avoid limit cases and degenerate cases, which means that I'm considering that all the points that are the end points of the lines are distinct. That is not a big deal to deal with connected lines. In the book, the algorithm that is presented is general at this level. Second thing, I'm not going to consider lines that overlap, that have more than one point in common. Okay, so I will not consider the case here, for example, where I would have one line here and another line which would be, let's say, here, and which have both line a segment in common, or the whole line in common. We do not consider this degenerated case. The last degenerated case that we will not consider here is the case where the lines is exactly horizontal. So if the line is exactly horizontal, we will not consider it for now. Again, this is not, those limit cases are not very dramatic in terms of implementation, but I will just present an implementation that is simple in order you to understand. Let me put it that way. The second podcast for this course will be an implementation of that thing, because computational geometry is not about theory. It's essentially about, of course, building good algorithms, but at the end of the day, we want you to code those things. And even though this algorithm will kind of look very simple and easy to understand, its implementation is far from being simple. And now, so the second part of the podcast will be a C++ implementation of this algorithm. Okay, so let's go on now. Okay, so we got a series of lines. Okay, and we look for all their intersections. First, we could find a greedy algorithm. So we have lines, or a series of segments, S1 up to Sn. We have Sn segments, and we could build a n squared algorithm that simply takes all the lines and try to find all the intersections with all the other lines. Okay, so it's exactly n square intersection computations, which is of course very feasible. But if we think about, let's say, 1,000,000 lines, so if we have 10 to the power 6 line, it will ask 10 to the power 6, okay, multiplied by 10 to the power 6 equals 10 to the power, 10 to the power operations. So if n equals, it would require 10 to the 12th operation, knowing that intersecting 2 lines, finding this intersection, is not an operation that is, it certainly requires about 100 floating point operation. And knowing that my computer is able to do, let's say, something like a 10 to the power 9 flops floating point operation per second. That's the order of magnitude. It would take a day to compute all the intersections using such an algorithm. So we don't consider the greedy algorithm, but if you were to do it by yourself, maybe you would do that in this course. The first thing to do when you want to understand such a more complicated algorithm is to start to program the simple one and try to see if you get the same solution as if the more complicated algorithm gets the same solution as the simple. So we are not considering the greedy algorithm. We're going to consider an algorithm that is of a class of, there is a class of algorithm called sweep line. Okay, this is a class of algorithm that is very common in computational geometry. And what is the principle of this algorithm is two things. There's two ingredients in the sweep line algorithm. The two ingredients are a sweep line. There's the three-dimensional version of those algorithms, a sweep plane. Okay, and the second algorithm is the second ingredient of a sweep line algorithm are events. So essentially, the sweep line algorithm consists in having a line, and here, for example, it's considered the upper part of my ruler here is my line, and we choose a direction on the sweep line. It could be vertical, horizontal, oblique. In my implementation, I just decide a priori that my sweep line algorithm will sweep the plane vertically, going from up to bottom. Okay, so my sweep line will browse, will sweep the plane from top to bottom. Okay, like that. So I'm starting here and here. So second thing, events. So what are events? In the sweep line algorithm, the events are the only positions of the line. So it's positions of the line. Okay. Line where the algorithm actually does something. So it means that the algorithm, the sweep line algorithm, will go from one event to the next event, okay, and between events nothing happens. So the events are the only places in the algorithm where things happen. So here, events are of two kinds in our algorithm. We have three kinds, let's put it that way, three kinds. We distinguish up to bottom, remember? Okay, up to bottom. So we sort all the endpoints, okay, of our lines in two categories. So sorry, I did just something wrong here. Okay, oops. Sorry. Okay. Go back to the layouts. Sorry. I want black lines. Okay. So yeah, like that. Okay, and last line like that. Okay. And so we have three kinds of points. The points that are the upper points of every single line that is considered. Okay, so we have n upper points. We also have n lower points. And we have here I intersections. So the number of intersections can go from 0, if the lines is very small, for example, with respect to the size of the domains where they lie, and the planar domain where they lie. And let's put it that way, the maximum amount of lines that the intersection that we could imagine is of the order of n. So a simple case, if we had lines like that, okay, and other lines like that, okay, so the number of intersections would be approximately n squared over 2, okay? So, excuse me, that's quite stupid. Okay. So if you have n lines, okay, we have here n over 2 lines vertical, n over 2 lines horizontal, and every horizontal lines intersects n over 2 vertical lines, and every vertical lines intersects n over 2 horizontal lines. So the I could be of the order of n, okay? And so it goes from 0 to n, okay? Those are lines. You can never have more than n intersections here, okay? So that's the setup. We have 3 kinds of points that we call events. These are the only issues, the only places when the algorithm, when the sweep-line algorithm, we do actually something. It's when the line encounters an even, and it could be the upper line, the upper point of one line, the lower point of one line, or an intersection point. Of course, intersection points will be created on the fly by the algorithms. So this is our setup for intersecting all the lines. So I'm going to try to copy the thing a little bit lower. Okay, so that, okay, and I'm putting my lines. Nice. Okay, so now what is the principle of our sweep-line algorithm? First, we are going to define 2 data structures. So 2 structures where we're going to store our data. The first is a priority queue. What is this priority queue? It stores events with a priority. So events will be stored. So events here are essentially points, green, red, or blue, upper points, lower points, intersection points. And the priority is the first event of the queue is the one that is the higher in the plane. Okay, so the priority is the higher, the first. So technically, we are going to use a binary search tree. And more specifically, if we go in C++, we're going to use in the standard library an object which is called a set of events, okay? And even will be a data structure that is going to be described in the second podcast, okay? So that's it. So it means that this set is always sorted in memory, and it takes of the order of log of the number of even, okay, to insert any new even in this priority queue, and taking the first one, okay, the highest one, takes one operation, of the order of one operation. So this is the setup. So we have a priority queue, we call it Q. So Q is our priority queue. So the priority queue stores every event. So it stores the event. So the algorithm will look like that. While not queue dot empty. Sorry, I want to write it straightforward. Okay. Okay. So we take the even at the top of the queue, we pop out the even from the queue, because we're going to treat it only once, and we are going to treat the even. Okay. Okay. This is pretty much how things are going. So how do we see a sweep line here? The sweep line is simply the fact that we take first this even, okay, and we treat it. Then we treat the second event. Then we're going to treat the third even, the fourth even, fifth, etc., 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 up to the point where we have treated all the events. So now, how can we detect intersections? So there is a need for a second data structure. So we have first a priority queue. Two, we have a status of the sweep line. We're going to have a data structure that contains what we call the status of the sweep line. So what is the status of the sweep line? Okay. So let's take that. So imagine the sweep line is at this position. Let's try to be as straight as possible. Like that. Okay. That's my sweep line. Oops, sorry. Okay, that's my sweep line, and it goes downwards. Okay, that's my sweep line. So the status of the sweep line that we call in the book T, or the status of the sweep line, is an ordered list of lines that actually intersect the sweep line, and this ordered list of lines goes from left, okay, to right. So the status show, okay, is going to contain all the currently intersected lines of my set of lines that are currently intersecting the sweep line. So if we look at the sweep line as drawn here, we have here essentially it's going to be S4, the first one, then S1, okay, then S2. Okay, those are the sweep line status. What is super important now to understand is that at any point, okay, when we are there, we assume that we have already computed all intersections above the sweep line L have been computed. Okay, so all the intersection above, for example, that point, is done. And all those ones here is to be done. Okay, that's the principle. So what can we say now? What can we do? We are going to go to the next even. Okay, so the sweep line at the position where I put it essentially does nothing, because we only do things when we are at an even. So what happens when we are at an even? Okay, so what happens when a sweep line what happens when the sweep line hits the next event? Okay, so what happens when the sweep line hits the next event? I'm going to try to copy that thing lower again. Okay, that's it. So yeah, right, perfect. So what happens when the sweep line hits the next event? We have classified the events in three categories. So we have three cases. One, next event is an upper point. It's not going to be the case here. When it's an upper point, what do we do? A new line, it means that a new line enters the status. So, okay, a new line enters the status. So we insert a new line. Let's put it that way. Okay, a new line. A new line. SK enters the status. There's a new line entering the status. Okay, so it means we insert SK into toe in its right position. Of course, it has to be, of course, the status has always to be sorted from left to right. So we put it in its right position. And then what you have to understand is when we are at a point, for example, imagine we have when the sweep line goes down, okay, you have to acknowledge, and this is the basic of this algorithm, that when you have two lines like S1 and S2 that are consecutive, okay, consecutive in the status, only consecutive lines can have intersections, okay, when a sweep line is at that level. So it means that here, when I have S1, S2, and S4, when I'm here, I will only compute intersection between, okay, the lines, okay, that are consecutive in the status. Then, when I will go to an intersection, things will happen, the ordering of the status will change, and a new intersection can be computed. So to be clear here, when I am intersecting, okay, when I am adding a new line in the status, I'm going to, so the status, excuse me, the status here will look like that. So the status is going to be SK1, 2, SKM, okay, SK, SKM plus 1, etc. Okay. What I am going to do is to look for intersections of those two lines that are consecutive in the status and those two lines. And if there is an intersection that is below the sweep line, if there exists intersection below the sweep line, then insert new events in the queue. Okay, so this is the first kind of event. If we have an upper point, we insert the new segment into the status. Second, we take in the status the segment which is exactly on the right and exactly on the left of the new segment, and we look for intersections that are above the sweep line. If those intersections exist, we simply insert them inside the queue. So second possibility, let's again take this graphic below. Okay. So second possibility, we have event is a lower point. So if the event is a lower point, it's, of course, we remove okay, the SK from the status. Okay, because the whole line now is above the sweep line, so it's not intersecting the sweep line, so it goes out. Yet, imagine that the situation before was like that. Okay, so this one is the one in the status we want to remove. At the end, we remove it. Okay, but at this point, SKM plus 1 become both, okay, successive in the status. It means that they may encounter an intersection. Okay, so here, compute intersection between SKM and SKM plus 1, okay? The ones that are now consecutive in the status because we've removed SK, so there's a new set of points, that set of line, new pair of lines that are consecutive. And if the intersection exists, if it exists, then add it. If the intersection exists and it's below the sweep line, and add it in the queue. A new event is there. So, third kind of event, again, I'm going to use my tool to move that downwards. Okay, so let's put it there. Okay, oops. So I just destroyed my, okay, it seems I destroyed my graphic, so I'm going to do it again. Okay, I'm too far for that, so imagine now, doesn't matter, okay, these are the upper points, okay, these are the lower points, and these are, so we have changed the color, you can understand these are the intersection points. If my event is an intersection, okay, which means that the sweep line is there, okay, the sweep line is somewhere there. What happens? So look here before. Let's draw the sweep line. That was the sweep lines just above. And when we go to the intersection, just below is going to be somewhere here. Okay. So what happened to the status of what happens to the status when we go from L here to here? Okay, when we go from above the intersection to below the intersection. What has actually happened is that if this is S1, okay, and this is S2, we had tau was having before S1 and S2, okay, and becomes, that was before, okay, after crossing the event, tau becomes the same, but S2, S1, okay. So what happened here is that the status of the sweep line is just slightly changed. We have just exchanged the two lines that were, in fact, creating the intersection here. So this intersection has to know about the two lines it is actually the intersection of, and in the sweep line, where we the status of the sweep line, we exchange that. But imagine that we had that situation before. Okay, SK1 to SKM, S1, S2, SKM plus 1, etc. That was before. After, we have that situation, SK1, and then SKM, S2, S1, SKM plus 1, up to the end. We don't have to check that thing, of course, because that thing is the intersection that is here. We don't have to do that. But before, we already had computed those two intersections. That is done, okay? But after having swapped the two lines in the status, we now have to compute possible intersection of those two ones and those two ones. Of course, we also have to do intersections. And if those intersections exist and are below the sweep line, then we have to add them in the even queue. Okay, so, as a résumé of the situation, we have to keep in memory two data structures. One is the even queue. Second is the list of lines that are actually intersecting the sweep line that we call the status tau. These are the two data structures, okay? So the idea is simply to go from one even to the one which is just below and treat this even in three different fashions, whether it's an upper point, lower point, or an intersection point. The only thing that we have to do when we treat these events is to reshape the status, add one line if it's an upper point, remove one line if it's a lower point, or swap two lines if it's an intersection point. And whenever we create two neighboring lines in the status, we have to check if those neighbors have intersections. Okay, when you program this thing, you are sure that you will find all the intersections points. So I'm going to finish for just the description of the algorithm for now, and the next podcast will be about implementation. Thank you for your attention.